Welcome to my video. My name is Ling Guo. I'm a PhD candidate from University of Oklahoma. Today I'm presenting our paper, Managing Conflicting Water Resource Goals and Uncertainties in a Dam Network by Exploring the Solution Space. First of all, why do we need dams? Dams are used to better manage water resource to suppress floods and drought, conserve wildlife, and provide water for human use in different ways. But does our socio-ecological system reach sustainability through operating the dams? The answer is no. In the 21st century, floods accounted for 44% of deaths caused by natural hazards, more than any other natural hazard, whereas drought caused a $20 billion loss a year in the United States alone. And since 1989, extinct freshwater fish in North America has increased 25%. We should and we can do better. We select a test problem, the Red River Basin. The Red River forms a short border between Texas and Oklahoma, then a shorter border between Texas and Arkansas. Then it enters Arkansas and then Louisiana. We select the first 14 dams due to the data accessibility. We need to ensure the demands from multiple user groups. The decisions we can make include water flow plans, model improvement, and system improvement. The system encounters uncertainties in inflow and outflow of the water. Our hypothesis is, by exploring the solution space and improving the model, we can make the dam network satisfy all user groups and be sensitive and be relatively insensitive to the uncertainties. The water in each reservoir behind each dam changes like this. The water storage in time t as the inflow subtracts the outflow is the water storage in time t plus 1. The inflow includes the water from upstream and the tributary and the precipitation. The outflow includes water for human use, wildlife reservation, evaporation, and seepage. In each reservoir, there are an inactive pool, a conservation pool, a flood control pool, a surcharge pool, and the maximum design surface. The actual upper and lower bound of a reservoir are the two red lines. Through controlling the water level between these two lines of all the reservoirs, we realize the functionalities of the dam network. We want to answer three questions. First, how can we manage multiple conflicting goals with evolving priorities? Second, how can we pinpoint the segment of the dam network that is sensitive to the uncertainties in the inflow and outflow? Third, how can we improve the system physically to be robust to uncertainties? We propose a post-solution analysis method with these three steps and particularize it to our test problem. As we happen to have three goals, we use a ternary plot to explore the weight space of the goals. If we have more than three goals, we need to do some analysis to identify the orthogonality among the goals and do some clustering analysis to reduce the dimension. If we cannot reduce the number of the clusters to be less than 4, we may use some other visualization tools, such as radar chart, to visualize the interrelationship between the goals. The details are in my next paper. Anyway, as we happen to have three goals, in each ternary we use each side to represent the weight of a goal, and we use colors to visualize how we approach the target of the goal. Blue means we achieve the goal very well. Red means we are far away from the target. And we identify an acceptable value for the goal that maintains the sustainability of the socio-ecological system. So the area between the acceptable value and the best point is the weight range to satisfy the user group of this goal. We do this for all three goals. Then the superimposed area is the weight range to satisfy all three user groups. Through running our model in iterations together with the next two steps, model improvement and system improvement, we shrink this area because we get rid of the area sensitive to uncertainties. The whole process is called design preference exploration, and we use it to answer the first question. We incorporate different uncertainties in water inflow and outflow. Here we only show the inflow scenarios. and act a sensitivity analysis and identify the reservoirs with restrictive upper bound and lower bound, and a dam that blocks the system from better serving the community of multiple user groups. Hence, we answer the second question. Through sensitivity analysis, we can pinpoint the sensitive and improvable segment of the system. Thus, we can adjust the model accordingly to improve its robustness. Given that we know the sensitive and improvable segment of the system, we explore the feasibility of physically changing the bounds of the reservoirs and relax the constraints. Then add a buffer in the mathematical model so we can bring the solution away from the physical boundary, which makes the system relatively insensitive to the uncertainties that result in the boundary variation. Thus, we answer the third question. After 3 iterations, we improve the system performance and robustness at the same time. In this figure, we visualize this improvement. We want to reduce the active constraint that are the constraints with zero slack or surplus, and then remove the improvable constraints that are the constraints with large due price. The size of the bubble represents how far a solution is away from the target of the goals. So we want to bring the bubble from the up right to the bottom left, meanwhile reduce its size. We did this in 3 iterations. Through exploring the solution space, we can finally make the socio-ecological system sustainable. Thank you for your listening. Welcome to explore my webpage.